Let's conclude with a brief review about null space and column space of a linear transformation. So, to take a concrete example, let's consider this linear transformation T, which maps each point x comma y comma z down to the closest point on this green plane to that original point x comma y comma z. So for example, this point xyz over here gets mapped down to that point, which I've called T of xyz, which again is the closest point on the green plane to the original point. So we can see that this map T squishes three-dimensional space down onto this green plane. Okay, the range of T is the set of all the points or all the vectors in R3 that get mapped to by some vector in R3 by T. And you can tell geometrically by the way we defined T that that's going to be exactly equal to this green plane. So every point on the green plane gets mapped to by at least one point in R3. And that's the column space of the corresponding matrix that represents this transformation. They're the same thing, the range of T in the column space of A, if A is the matrix that represents T. Now, the null space of A is going to be the set of all vectors that get mapped to the zero vector. And geometrically, you can think about where a point would have to be in order to get mapped to the origin over here. And you can see that it's going to have to be somewhere on this pink line, which I've drawn over here on the domain side to make it really clear that the null space of A lives on the domain side of this picture. So that pink line is the perpendicular line through the origin. It's perpendicular to the green plane. And you can see that any point on that line is going to get squished down to the origin, and any point off that line is going to get squished down to some different point that's not the origin. In the context of linear transformations, we call the null space the kernel. So for matrices, we have null space and column space, and for the corresponding linear transformations, we have the kernel and the range. So let's make a little list of some comparisons between the null space and the column space. So first of all, as we said, the null space is the same as the kernel and the column space is the same as the range. If A is an M by N matrix, then the null space of A is a subset of Rn and the column space of A is a subset of Rm. This is because T is a linear transformation from Rn to Rm, and the null space lives on the domain side of the picture, and the column space lives on the codomain side of the picture. Vectors in the null space are harder to find than vectors in the column space because you need to solve the linear equation Ax equals 0. That will give you some x's that map to 0. Those will be in the null space. But that involves a solution process. Vectors in the column space are easy to find. The columns of A are in the column space by definition, and any linear combinations of the columns of A are also in the column space, so they're very easy to form. Conversely, if you have a vector and you want to check whether it's in the null space, that's easy. You just multiply A times X and check whether you got 0. If so, it's in the null space. If not, it isn't. Checking whether a particular vector in the column space is a little bit harder because, again, it requires a solving step. We have to determine whether the system Ax equals y is consistent. If so, then there's some x that maps to y, and y is in the column space. If there's not, then y is not in the column space. Lastly, the null space is equal to the space containing only the 0 vector, if and only if A is injective. And in matrix terms, we recognize that by checking whether A has a pivot in every column. On the other hand, the column space of A is equal to Rm if and only if T is surjective, which we check in matrix terms by seeing whether there's a pivot in every row.